Hello everybody, I am Hari. Welcome to my class. So today we are going to learn about cyclic structures of monosaccharides. So in our previous class we have discussed about the open chain structures of monosaccharides by using Fisher projection formula, right? So today we are going to learn about the cyclic structures of monosaccharides. So why should we learn about the cyclic structures? It's important to know because as we are expecting, the monosaccharides they just do not exist as open chain structures even in our body. That is in the physiological conditions also. Mostly the monosaccharides exist in the form of the cyclic structures or the ring structures. So it's important to know about the cyclic structures of monosaccharides. So let's know about this today. Okay. So in the aqueous solutions, monosaccharides they exist as cyclic structures or ring structures. So when this monosaccharides they exist as open chain structures, they undergo certain reaction. And after that reaction, the open chain form, it will be getting converted to the closed chain structure. Okay, so how does it happen? Let's know. If we take the case or if we take the structure of any monosaccharide, generally we all know that which contains the, for example, if we take the case of aldoses, which contains the aldehyde group as a functional group, then chiral carbon atoms, and finally it contains the primary alcohol, right? So in the case of ketoses, which contains two primary alcohols at both the ends and one ketone group as the functional group and the remaining chiral carbon atoms, right? So here if we take either aldoses or ketoses, the functional group carbon is called a carbonyl group. So that carbonyl compound, that carbonyl carbon which forms the covalent bond with OH, the carbonyl carbon, it forms a covalent bond with oxygen of any of the OH groups within the same structure. So the carbonyl carbon, that is the functional group carbon, which forms a covalent bond with oxygen atom in the OH, in any one of the OH groups that is present in the same structure. So it leads to the formation of structures called Hemi Acetols or Hemi Ketones. When the reaction occurs in the aldoses, it leads to the formation of Hemi Acetols, and if this occurs in ketoses, then it leads to the formation of Hemi Ketols. So if you observe these reactions, this is the aldehyde group. So here R indicates the remaining chain of the monosaccharide. So this is the first carbon containing the functional group, that is aldehyde, and the remaining whole chain is represented as R2. And as we have discussed, the Hemi Acetols and Hemi Ketols, why they are forming? They form the covalent bond within the same molecule, right? So here the OH group is also from the same monosaccharide unit, and here we are considering the remaining chain as R2. Okay, so here with this oxygen, here the carbon forms the covalent bond and it leads to the formation of this structure, and this is called Hemi Acetol. In the same way, this is the structure of a ketone molecule. So this C double bond O is the functional group, and the above structure, because it is in the second position, right? So the first carbon is represented as R1 and the remaining chain is represented as R2. But here also within the same chain the covalent bond occurs. So here OH and the remaining whole chain is represented as R3. Now the covalent bond is formed between the oxygen of this OH with this carbon. It leads to the formation of Hemi Ketone. And with the help of these structures, the open chain structures of monosaccharides, they will be converted to cyclic structures or ring structures, and they are most predominant in cyclic forms in the aqueous solutions. So let's understand about the cyclic structures with the help of an aldose and the ketones. After the formation of Hemi Acetols and Hemi Ketols, we can see the carbonyl carbon, it gets one more asymmetric carbon. It becomes an asymmetric carbon because in the open chain structure, if we observe the carbonyl carbon, that is the functional group, it generally exists in the form of an aldehyde group, that is CHO. Since the carbon is attached to oxygen with a double bond, we cannot consider this as the chiral carbon atom. But if we observe the Hemi Acetol or Hemi Ketol, since this kind of transfer occurs, that is the covalent bond that occurs between the oxygen of one of the OH groups and the carbonyl carbon, it leads to the formation of the chiral carbon at the first position. So that's why if we compare open chain structure and the closed chain structure, for the closed chain one, at the carbonyl carbon, we can see it becomes a chiral carbon atom. So because of that, it exists in two forms. So those two stereoisomeric forms are called alpha form and the beta form. So let's understand that with the help of an example, that is D-glucose. Okay, so in the aqueous solutions, D-glucose generally most predominantly exists in the form of a cyclic structure or a ring structure. So how does it form? Means here if we observe the open chain structure of D-glucose, as we all know that D-glucose is an aldohexose, so which contains aldehyde as the functional group and 6 carbon atoms. So here the first carbon is the functional group, and coming to the 5th position, the last chiral center, whatever it contains the OH group, that oxygen in this OH group, it forms a covalent bond with the carbon atom at the first position. So here the bending occurs and it leads to the formation of this particular structure. So any of these two. So both of these are the ring structures. So here in the case of D-glucose, the Hemi Acetol is formed by the reaction between C1 and the OH of C5. So it leads to the formation of a 6-membered ring. Why we are saying it as a 6-membered ring? Because this ring structure includes 6 atoms. So let's count them. 1, 2, 3, 4, 5, 6. So including oxygen, this ring structure contains 6 atoms. So if we observe the shape of or the structure of this ring structure, this resembles the 6-membered ring called Piranha ring. So since it is resembling the structure of Piranha, we are calling these structures as Pyranoses. Okay, 6-membered ring structures are called Pyranoses. So this is the pyranose structure of glucose, so that is why we are calling it glucopyranose. Then what is the difference between alpha and beta? Because if there is no difference, we cannot have two structures, right? So the main difference between these two structures is, while it is forming the Hemi Acetol structure, the OH group that is going to be formed at the first position, it may get attached either towards the right side or towards the left side. Okay, so because of the positioning, it is leading to the formation of two structures. Here we can see, while it is forming the ring structure, if the OH group is towards the down, it is nothing but towards the right side. If it is on the right side, it comes down, right? So if it is getting attached towards the down position, that is opposite to the primary carbon, then this structure is called alpha form. It is just not for glucose, it may be even a furanose, whatever it may be. For this ring structure, if the OH is towards the downside of the carbonyl carbon, then it is called the alpha form. So it is alpha D glucopyranose. Coming to beta D glucopyranose, here the OH group is attached at the upper side of the carbonyl carbon, that is towards the left side here. Okay, so when these two molecules are towards the same side, that is OH on the carbonyl carbon and the CH2OH primary alcohol on the same side, then that structure is called beta-D-glucopyranose. Okay, I hope you understood. Pyranoses are 6-membered ring structures. It is because of the formation of a covalent bond between C1 carbon atom and OH of C5 carbon atom. It leads to the formation of a 6-membered ring structure that is called pyranose. Okay, because of the Hemi Acetol or even Hemi Acetol formation, the carbonyl carbon, it becomes a chiral carbon. So it leads to the formation of 2 stereoisomeric forms, because these two are isomers, stereoisomers. They have the same structural formula but just difference in their position of a particular atom, so a particular group. So these two are the 2 stereoisomers that glucose has. See, as we have discussed in our previous classes, the open chain structures, we can write down the open chain structures by using Fisher projection formula. Then it is easy for us to understand, right? In the same way, even for the cyclic structures also, we mainly depend on a kind of projections. Those are called Haworth projections. So by using Haworth projections, we can know the stereochemistry of ring structures of the monosaccharides. So according to Haworth projection, if we observe the plane of the ring, it is same not like this as we have drawn on the board. Okay, so the plane of the ring is perpendicular to the plane of the paper or board. So here this is the plane of the board, right? But if we observe this ring structure, it is just not like this. It is perpendicular. So we have to imagine that whatever the thick lines that are drawn here, it indicates that the ring structure is not like this, but it is like this. Okay, so here we can see the ring. Okay, so which is perpendicular to the plane of the paper or plane of the board. What about the additional groups? The atoms that are attached to this ring are, one is towards upper side and the other one is towards down. One is up, another one down. So this way the atoms or groups will be attached to this pyranose ring. So this was proposed by Haworth projection. So since it is difficult for us to understand and it is difficult for us to draw them on the board, we are just indicating with the dark lines, which indicates the ring is, the plane of the ring is perpendicular to the plane of the paper or board. Along with these structures, although exoses, even they can exist in the form of 5-membered ring structures called Furanoses. Why we are saying those are Furanoses? Because those 5-membered ring structures, they resemble the structure of Furan ring. So those are called Furanoses. So here Furan, which includes 5 atoms, 1, 2, 3, 4, 5. So here in the same way, the Furanoses, they include 5 atoms. In the case of Pyranoses, we have seen the Pyran ring. Pyranose is formed by the Hemi Acetol linkage between C1 atom and the C5, right? But in case of Furanoses, instead of C5, we can see the OH group of C4 carbon atom. There is an oxygen of OH at C4 position. It forms the covalent bond with C1. Even here also it leads to the formation of chiral center, but the ring structure will not be the pyranose, it will be furanose. Okay, so even although exoses, they can exist in furanose form, but comparatively they are more predominant in pyranose structures in aqueous solutions. So we have discussed about the pyranose structures and furanose structures of aldohexoses, right? In the same way, even ketohexoses, they exist in both the forms, furanose forms and pyranose forms. So let's know about the furanose forms. So here if we observe the structure of D-fructose, that is a ketohexose, if we observe the structure, the first and the last carbons are the primary alcohols and the second carbon contains a functional group, that is the carbonyl atom is the ketone here, and the remaining are the chiral centers. Here if we observe the structure, the Hemi Acetol formation occurs between the second carbon, that is the functional group of this compound, and the oxygen of OH group at fifth carbon. So which includes the 4 atoms. 1, 2, 3, 4. So from here the molecule will bend down here. Okay, so this is the first one and this is the second one and this is fifth one. So from the fifth one, when it is bending like this, it leads to the formation of 5-membered ring structure. So this is the Furanose, which resembles the structure of a ring called furan. So that is why we are calling these as Furanoses. And these Furanoses include 4 atoms in the ring structure. Those are 1, 2, 3, 4. First one and the last one will be towards the upper positions. And here also we have 2 stereoisomers because it leads to the formation of chiral center. So that is why we will get 2 stereoisomers. So those are nothing but alpha form and beta form. So alpha form, here the OH group, it will be positioned at the downwards. So here the OH group will be positioned at downwards, and which is opposite to primary alcohol at 6th position. So it is alpha D fructofuranose. Here the OH group is positioned upside and which is in the parallel direction of CH2OH, that is in the same direction like primary alcohol at 6th position. So this is the beta D fructofuranose. Okay, so in the same way, even ketohexoses, they exist in pyranose forms. Those are 6-membered ring structures. In aqueous solutions, fructose exists in a pyranose form, and in its derivatives, it exists in furanose forms. So let's know even about the pyranose structures of fructose. So here, Furanoses between C2 and C5. For Pyranoses between C2 and C6. Here, in case of Furanoses, the covalent bond occurs between C2 and C5, that is C2 and C5. But in case of Pyranoses, it is between C2 and C6. C2 is common because it is a functional group that is located at the 2nd position. So between C2 and C5 leads to Furanose formation. Between C2 and C6 leads to Pyranose formation. So already we have discussed about Furanoses. So let's see how the pyranose structures of ketohexoses exist. So here from the here the OH group at 6th position, it forms a covalent bond with the carbon at the 2nd position. So from here the bending occurs and it leads to the formation of pyranose structure, and this pyranose, which includes 6 atoms, so that is 1, 2, 3, 4, 5 and 6. Okay, so since it occurs between the 2nd position and the 6th position, so 2nd, 3rd, 4th, 5th, 6th. And you may get the doubt why we are not writing CH2OH here. It is ketose, and at the 6th position, when OH is left, it leaves only 2 hydrogen atoms. So one will be upside and another one will be downside. So when OH is towards at the bottom side, that is downwards, then it is the alpha D fructopyranose. If it is on the top side, that is beta D fructopyranose. Okay, so as we have discussed already, fructose, it is most predominant in pyranose form when it is in the aqueous solution, and when it is in the derivatives, when it comes to its derivatives, it is most predominant in furanose form. So coming to certain examples like ribose and deoxyribose, they are most predominant in furanose forms, that is a 5-membered ring structure that we can even observe in DNA and RNA, right? So those are pyranoses and furanoses. Coming to anomers. Anomers are the isomeric forms of monosaccharides that differ only at the Hemi Acetol or Hemi Acetol carbon. Those isomers are called anomers. So if we observe here, alpha D form and beta, these two structures are, they both have the same structural formula, but just differ at carbonyl carbon. Only at that particular position these two get differ. The remaining whole structure will be same. So the isomeric forms of the monosaccharides that differ at the carbonyl carbon, that is Hemi Acetol or Hemi Acetol carbon, those isomers are called anomers, and that particular carbon atom is called anomeric carbon. So for ketoses the anomeric carbon is second one, and for aldoses the anomeric carbon is the first one. So these two forms, they are interconvertible when they are in the aqueous solutions. So this interconversion occurs by the process called mutarotation. So as we have already discussed, alpha form and the beta form, those two are interconvertible when they are in the aqueous solution by the process called mutarotation. So when they undergo interconversion, it leads to the formation of equilibrium mixture, right? So when we observe the equilibrium mixture, which contains almost 1/3 portion, that is around 36% of alpha form and around 63% of beta form and less than 1% of open chain structure. So here we are taking the example of glucose. So if we observe the equilibrium mixture of glucose, which contains 36%, so this one we were discussing about the equilibrium mixture, okay. So 36% of equilibrium mixture contains glucose in alpha form, that is alpha D glucopyranose, and 63% of this equilibrium mixture contains beta D glucopyranose, and the remaining 1% or less than 1% of this equilibrium mixture contains open chain structure of glucose. Okay, so this is all about the Hemi Acetol, Hemi Acetol formation and Pyranose structures and Furanose structures, that is the cyclic structures by using Haworth projections and the anomers of monosaccharides. Hope you all understood. If you have any questions to ask, please mention them in the comment section. Thank you.